Okay, so let's solve this test question. A couple points. This is something I wrote. I just want to point out a few things. Number one, I break these into concepts. So right there, you kind of know what to use, and that's not really realistic. In the real world or in a normal test, you may not know the best principle to use here, but here I should use the work energy principle. Number two, if you approach this problem with the by looking at the picture and reading the diagram and saying, okay, it's an inclined plane. I need an inclined plane solution. And I'm going to look up an inclined plane solution. There's like a million different kind of problems that are completely different that all deal with inclined planes. That's not the type of problem it is. That's the context. Okay, so just because it has a plane doesn't mean that you have to find the acceleration or that you use momentum or force equals mass times net force equals mass times acceleration. It depends on what you're solving for. So you don't want to look at those superficial things. You want to look at the actual problem. And like I said, this says work energy. Okay, so let's scooch up a little bit. Let's just start reading the problem. A block of ice, no friction. That's cool. Mass 15.5 kilograms. So M equals 15.5 kilograms. So one of the things I find is that even though it says it right there and you could underline it, just writing it off to the side kind of helps you organize all your ideas and kind of verify that it's there. Okay, so it's pulled up by a rope with a force of 85 newtons. So this is 85 newtons. So let's just say the magnitude of the force, let's call that the tension. T equals 85 newtons. Now I wrote that as a scalar quantity because I don't want to write it as a vector right now. So I didn't put the arrow over it, and that's a scalar. 14 degrees. I got that right there. I'll just leave it there. And the plane is 23 degrees. It didn't say that, but it's right there in the picture. As shown below. Calculate the work done by the gravitational force in this motion, as well as the work done by the rope, and then find the final speed. So let's start with the work done by the rope. I give the answers. That's right. I was having problems with this. So, I don't really care about the number, right? I care about the solution. So let's start with the work energy principle that says the work is the change in energy, and I need to pick my system, and I'm going to pick my system of the block. So that means I need to look at all the forces acting on the block and calculate the forces by those. So let's say I have this situation. Let's draw the forces right here. I have the downward pulling gravitational force. I'm going to write that as a vector, and I'm going to write that as a vector. Now that can't be the only thing. There's also this. Okay. And so I have those three forces, and they do not add up to zero, the zero vector, because, well, we don't know. Well, I do now because it says the final velocity is 3.74, so it's speeding up. Okay, so it has an acceleration. Okay, so if I have that as my system, I need to calculate the work done by, I'll put this work gravity plus work tension plus work normal force equals the change in kinetic energy, where kinetic energy is 1/2 mv squared. That's change is very important. You cannot say kinetic energy. If you write this out and you say, oh, the initial kinetic energy is 0, so I'm just going to put kinetic energy. Okay, you'll get the right answer, but it's wrong because it's the change in kinetic energy. So let's write expressions for work in general. Work is equal to the force times the displacement times the cosine of the angle between them. So in this case, I know my displacement is 4.7 meters. And each force has a different angle. So work by the normal force is going to be the normal force, which I don't know, times delta R, which I do know, times cosine of 90 degrees. So in this case, it's moving this way, but the force is that way. So that means that the angle is 90 degrees and cosine of 90 is 0, so no work done by the normal force. I don't need to find that normal force. Okay. Work done by gravity. This is going to be mg delta R cosine. Now I do need to find this angle. So it's moving this way. I need to find that angle right there. So if this is, we need to do a little geometry. If that's 90 degrees, this is 90 minus 23, so that would be 67. And then this is 180, so 180 minus 67 is going to be 113, right? Is that right? 113. And so now I can calculate the work done by that. Let's just go ahead and do that because I have it up there. So I'm going to put in my values. Oops. On. Oh, my thing. Calculator's loose. There we go. Okay. Memory loss, that's cool. Okay, so the mass was 15.5. 9.8 is the gravitational field. Delta R was 4.7. And then I'm going to do 113 cosine. 113 trig cosine. And you'll notice a negative number. It's very important, okay? And I get negative 270. I get negative 279. That's right. What did I write it there? Okay, that's what I got. Okay, joules. So because the block is moving this way, but the gravitational force is pulling in the opposite direction of its motion, it's actually working against it. Literally. Okay, that's why it's a negative work. And that's cool. It can be you can do negative work. Nothing wrong with that. Okay, now finally, the work done by the tension. I gave you this force. It was 85 newtons times delta R times cosine of, now the angle between those two is just 14 degrees. Cosine 14. So if I put that in my calculator, which my battery came out again, I need to fix this permanently. There it goes. Okay. So I'm going to say 85, 4.7, 14 cosine times. And that's a positive number. And I get 387.6 joules. So now my total work is going to be just these two added together. And so I'm going to get 279. Oops, that's wrong. Okay, so let's say, let's drop that. 279 change sign, 387.6 plus. Oh crap, I'm sorry. 279 change sign, enter. 387.6 plus. I get 108.6 joules. Okay. Now I can say that's equal to K2 minus K1, where K1 is the initial kinetic energy, which is 0. So now I can say work equals 1/2 mv2 squared. So V2 equals 2 times the work. This is the total work divided by the mass. So that's going to be 2 times 108.6 divided by 15.5. And I forgot to take the square root, right? Because that was squared. So I multiply both sides by 2, divide both sides by m, and then I got to take the square root. Okay, so let's get the final velocity. So I have the 108, 2 times 15.5 divided by, and then take the square root, which is right there. And I get the same thing I got before, 3.74 meters per second. And that agrees with that number right there. Because I wrote that, see? So it'd be really weird if I got something different than the thing that I wrote. Okay, so there you go. This is the complete solution. I already had the answer, so if you just wrote down those answers, you're not solving the problem, right? Let's put down the important things. That is super important. This is super important. That's a pretty important thing. And then these you could do, I mean, that's important to show, but it's not nearly as important. These, and that too. These are your most important things. This is just showing your work after that. So there you go. Work energy problem. It was unique. Not too difficult, though. Okay, that's it.